Hey again, everybody. This is the day 4 video about resistance and resistors. So first, we're going to take a look at both the real and schematic representation of resistors within circuits. Um, on the left, you see real resistors. I've got a picture coming up in just a moment. The schematic representation of resistors is kind of a jagged line. And this jagged line is trying to represent what a resistor does in a circuit. It is kind of a control against current flow. If we have a circuit of just wires, a battery for the voltage source, and then wires connecting one terminal of the battery around to the other, that circuit effectively has zero resistance, and that is something you do not want. Um, the resistance in a circuit again controls the current flow, and if you have no resistance, then you have theoretically an infinite current. When current gets too high, that's when you can cause electrical fires in a circuit, and that is how electrical fires start in houses. Is when um, for maybe too many objects are plugged in parallel to a circuit, drawing too much current from the source, and maybe if that circuit breaker doesn't flip fast enough, or maybe the circuit breaker was set to too high a setting that was safe, then an electrical fire could start behind the walls. Maybe combined with some bad insulation, touching wires, perhaps. Those are some common ways electrical fires can start in resident homes. But anyway, let's talk about the more theoretical stuff here instead of terrible ideas like that. Um, resistor is an object placed in a circuit intentionally to limit the flow of current. Now, a resistor can be an actual device like you see in these pictures here. Very small. It's only about the size of maybe about as long as a flash drive, and that's including the bits of wire coming out of the resistor itself. These objects limit the flow of charge. You see a little picture down on the left of circuits in a electric circuit board. Um, these resistors offer resistance, which is abbreviated mathematically as the letter R. Um, and like I said, they limit current flow. Now, not all circuits have a physical resistor in their circuit. An object that you plug in that you're trying to receive power to also acts as a resistor. This ranges from everything, fans, chargers, televisions, heaters, like I have here, your hair dryer. Anything you plug into an outlet, anything you hook up to a circuit has internal resistance, so it will not draw too much current from that circuit. But again, some actual circuits inside of, with circuit boards that are more complex than just plugging something into a source, have several resistors with them to limit the current flow in different parts of the circuit. I mean, this is a little bit of a complicated circuit, even though it's very small. You can see the pen up here for size. But there are plenty of resistors in this circuit. I mean, we've got one here, we've got one here, we've got a couple over here, another one here. You can see these resistors, doing their job to restrict current flow, so it's never too high in any one part of the circuit for safety features and to also make sure the components are behaving the way you want. All right, so let's talk about the resistance within wires. Of course, there are objects, like you saw a moment ago, called resistors that provide most of the resistance in a circuit, but wires themselves actually do have resistance. It's a very small amount, but it is an amount all the same. I'll get myself out of the way here. So we have a couple of factors that affect the resistance of wires, and you can think of really just like water through a pipe. It's a very similar idea to think of resistance through of electron flow through a wire, same as you think of restriction of water flow through a pipe. A couple of factors that affect the resistance of a wire is its resistivity. That's not the same thing. Talk about that again in a second. Resistivity, the length of the wire, and its cross-sectional area. And then a fourth factor that affects a wire's resistance is its temperature. We're going to only look at wires of constant temperature, but as temperature increases, the resistance of a wire does also increase. Good way to remember that is, if an object is left on too long, maybe even like your cell phone or a computer, and it gets hot, sometimes it starts to slow down. The actual circuit is slowing down, the current flow, because the resistance is going up. So resistivity, let's go to that one first. Resistivity and resistance, again, they are not the same thing. Resistivity is a property of a metal, the metal that the wire is made of. It's really just a value. It's just how intrinsically conductive is that metal. The conductivity and the resistivity of a metal are complete inverses of each other. So the more conductive a metal, the less resistivity it has. We can take a look at our physics reference table to see a chart of some resistivity values. So resistivity, you can find the chart in the tables on page 4. This is all resistivities at 20 degrees Celsius, about standard room temperature. We've got 6 different metals, and they all have different resistivity values. All metal wire resistivities are hovering around 10 to the negative 8 ohm meters. That's the unit for resistivity. And by the way, you see already the variable for resistivity is the Greek letter rho. It's kind of like an English P, but slightly more curved. So just taking a look at these numbers, the resistivity of these metals, it's all extremely low. And this is why we usually ignore the resistance of wires, because it's so little, especially when compared to resistors or hair dryers or whatever we're plugging in, that we can kind of ignore the wire's resistance. But again, it is there, and we did already mention the factors that affect the resistance of a wire. So let's take a look at how we can figure that out. Before we look at the equation, though, just take a look at the chart again. We've got aluminum, copper, gold, nichrome, silver, and tungsten. All these are raised to the negative 8 power, 10 to the negative 8 multiplier, rather. So just looking at the base number kind of gives us an idea of which of these metals are more resistive than the others. You can take a look here. The smallest number in this chart is the 1.59. That's the silver. Silver is the least resistant metal. That is, it's the most conductive metal. So how come we don't use silver for our electrical wiring? I'll let you think about that, and I'll ask you again at the exit ticket. So again, resistance in a wire. 3 factors that we're going to look at. Again, we're going to keep temperature constant. So we're only looking at the resistivity of the metal, the length of the wire, and the cross-sectional area of that wire. Let me talk to you about cross-sectional area first. Wires are cylindrical in shape. This is a pen, but it's got the same shape. The cross-sectional area is if you kind of chopped that object in half and then looked at what area you see. So it's not hard to figure out what the cross-sectional area of a wire is. It's a circle. So that is the cross-sectional area. So you can think of it like the thickness of the wire. So if we have a wire that's long, or if it keeps getting longer, the resistance of the wire goes up. It's tougher to go through a longer wire than a short one. The cross-sectional area, though, is opposite. If the wire is thicker, that means it has a wider cross-sectional area. Well, then it's easier to flow through. Again, just think of water through a pipe. So if we want wires to be the least resistant possible, we want them to have a low resistivity value. So, a good metal like silver. We want them to be short, and we want them to be wide. Those factors will all contribute to a low resistance wire, so you get the maximum current flow, so you're not burning any energy trying to fight through the wire itself. You want all the energy of the circuit to go into the light bulb or whatever you're plugging in. All right, so here is a lot of information that I didn't have segmented down like I usually do. So let's take a look at it all at once. Again, the cross-sectional area is the area of a circle. So now think about your area of a circle equation. Here it is, pi r squared. So when we see the a in the equation, we're thinking pi r squared. Again, the resistance of a wire is equal to its resistivity combined with its length, that is multiplied by its length, and then divided out by that cross-sectional area. Here it is in variable form. the resistance of a wire is rho, the resistivity, length of the wire, L, divided by the area cross-sectional, which is, again, is pi r squared. If you think of the units, resistance is measured in ohms, named after George Simon Ohm. The symbol for the ohm is the omega symbol. That is the Greek letter omega. Just conveniently, Mr. Ohm had a name that almost perfectly matched a Greek letter, so we decided to give the unit of resistance its name after him. So then the resistivity has units of ohms times meters, length is meters, area is measured in meters squared. Put them all together, you get ohms equaling ohms. It's, of course, always got to work out that way in any equation. You have the equation here. Let's take a look at an example. It'll make some more sense maybe. So let's say we've got a wire made of copper. Let's say it's 0.5 meter long with a radius of 0.1 meters. And we want to know what the resistance of that wire is at 20 degrees Celsius. So that chart of resistivities are what they are at that temperature. Well, again, here's the equation. We've got rho multiplied by L, then divide out the cross-sectional area. I'll show you this example again with the color coordination to match the colors of my equation here. So our 0.5 meter long wire, that is the length. Copper is going to tell us the resistivity. We have a radius of 0.1 meter, that's the R, within the cross-sectional area, being a circle. And we're looking for the resistance. Okay, so there's the equation again. I'm automatically changing it to adjust for the actual shape of the cross-sectional area, being the circle. So this A becomes pi r squared, the area of a circle. So I boxed this equation because this is the one that makes more sense. This is the general version, but since wires are cylindrical, their cross-sectional areas are circle, let's just go with this version. And now we're just throwing in our numbers. We have to look to the chart for the resistivity of copper, but if we do, we get 1.72 times 10 raised to the negative 8 power. Again, this is calculator business, but that's what they're for. 0.5 meters for our length, 0.1 meters for our radius. Only the radius is squared in the circle area equation. And of course, we got to multiply that by pi. Now, be very careful with these kinds of calculations. You've got to maybe just do it step by step in your calculator, or be very careful with your parentheses. I'm showing you parentheses in this example such that when you type in a calculator just like this, you can do it in one step. But always be careful whenever there's a lot of operations at once, especially when there's divisions and squareds and all these mathematical operations. But if you're punching this all correctly, you can try it out yourself. We should get about 2.7 times 10 to the negative 7 ohms of resistance within this wire. That is an extremely small number. I mean, we're talking about 0.00000027 ohms. Very negligible amount. Like I said a few minutes ago, that is why we don't really worry about the resistance in wires when looking at entire circuits. But this is how you would calculate the resistance in circuits, even in their wires, if you are truly calculating it to the very decimal of an ohm. That's the end of this video on resistance and resistance in wires. You can try exit ticket number 4, and I'll see you in the video tomorrow.